First of all, I apologize for the ruckus about the homework. I have no idea what happened. You've got a little bit of chapter 6 in there, you've got a little bit of chapter either 17 or 19 in there, and then you've got two pieces of this chapter, but not all of it. Consequently, you will only be responsible for 1 through 3. And number 3, what you were supposed to find was the number of electrons over that 3 hours that pass through that given section of wire. And I will be posting after this video, I'll be posting the rest of what that homework should have looked like, but you'll only be responsible for 1 through 3. All right, this chapter now we're talking about how can we go from potential energy, electric potential, to actually using the electric potential in a formal way. We talked about how to use it in the last chapter when we converted it from delta PEQ to delta KE or something like that. Now we're actually going to talk about making it useful by putting it in a circuit and harnessing it. We've already talked about if we're going to do a direct current circuit, then we have to have a battery to provide the electromotive force. We talked about the fact that there are two pieces of the circuit. The current gives me pretty much how many electrons are going through in a given time. And the voltage is how hard are these electrons being pushed in the direction that they ought to go. And we quantified that, and we talked about the fact that the flow of electrons is in the direction that they actually flow, but that we represent current opposite the flow of electrons. Thank you, Ben Franklin. And now we're actually going to talk about drift velocity. How really do those electrons move through a wire? Now remember when I was first teaching a 9th grade science course years and years ago, and the textbook I had showed a picture of these little electrons with feet and legs running along a wire, and it gave the impression that they were just flying across the wire. And I always had that in my mind for a long time. But the reality is that's not what they do. And there's a reason why we call it drift velocity. Now I've got some numbers here for you to consider. 1 times 10 to the 6th is actually the speed that electrons leave the atom or move through space. Leave the atom and randomly move. And we're talking about a metal here because that's what's going to be carrying the electron, something that is a conductor, which means it's going to be a metal. So 1 times 10 to the 6th is going to be meters per second. And it's the speed that electrons leave the atom and randomly move through metal. So it sounds like, wow, 1 million meters per second. That's kind of fast. Why is it that Mrs. Warner is saying, yeah, they don't actually have little feet that run? They don't really move that quickly because there is 1 times 10 to the 14th collisions per second. Per second. That's what the electrons make. They make that many collisions per second. And because of that, okay, that's my little therefore sign, remember that? And therefore, they're changing directions. So, yeah, it'd be nice if they just move that fast along the wire, but they don't. Because as they're trying to move, they are making this ridiculous number of collisions per second. And especially I want you to think about what you've learned about metals in chemistry. You've learned that ionic bonding happens because of the extreme electronegativity difference between a metal and a nonmetal. Covalent bonding happens, polar covalent bonding happens when, again, there's an electronegativity difference between them. And so there's going to be some charges, but then it talked about, well, okay, what do metals do? And you've heard the electron C theory of metals. And basically what happens is, in a metal, the outer shell, the valence electrons, particularly the S and sometimes the P electrons, are not really all that bound to the atom. because there's just not that much pull of the nucleus on these electrons. So they're not that bound to the atom, so they kind of run freely. Typically, they can run between the atoms, but typically they like to stay on the outside of the surface of the metal. That's why it's such a good conductor. So because of that, you have these free electrons running all over the place, and they are running into stuff, and they're colliding with stuff everywhere. And so because of that, they don't actually get to move 1 times 10 to the 6 meters per second. They are making these collisions 1 times 10 to the 14th collisions per second, and because of that, they're changing directions. They don't flow, they don't naturally, if I don't have a current, if I don't have potential difference attached to them, creating an electric field. If I don't have that, then they're just going to randomly move in all directions and make no net change towards any one thing. Because these collisions provide a resistive drag force. So now I've attached a potential difference to my wire so that there's a positive and a negative terminal, and there's a potential difference between the two of them, and that creates an electric field. So now the electrons are wanting to move towards the positive. They have a little trouble moving towards it because the collisions that are happening provide a resistive drag force. But because of the electric field. So there's something holding them back, but then there's also something drawing them in the direction of the positive terminal, and that is the electric field between the terminals. Because of the electric field between the terminals, I'm just going to call it E, between the terminals, there is a constant drift. Toward the positive. And I really want to emphasize the words drift. They're not flying to that positive, but there is a net drift towards the positive terminal. Now, there's a lot more I could be saying about this. Actually, because there is an attraction, a pull by the field of the electrons, that pull is a force. And it's going to cause them to want to accelerate towards the electric field. But there is that net drag, the drag force, that balances that out. So it starts to accelerate, and then as soon as it starts to accelerate, it comes up against this drag force. Those two are in equilibrium with each other. They're opposite but equal forces. And so you get a constant velocity, but it is not a constant fast velocity. And yeah, that's pretty much all I really want to say about this. Just something interesting that because it's a metal, because there's all these electrons running around all over the place, there's just so much that gets in the way that causes it to collide. But they are rather slowly moving in the net direction of the positive terminal. Now the drift velocity, that's my little d, my drift velocity is equal to d, which is going to be displacement, over t, and it's going to be much slower than the 1 times 10 to the 6 meters per second. We're thinking of it now instead of 10 to the 6, we're thinking of it in order of maybe 10 to the negative 3 or 10 to the negative 4 meters, something times 10 to the negative 3 or 4 meters per second. Negative 4 meters per second, a lot slower. And I want to emphasize the fact that d is not the distance it travels, d is the net displacement. All right, so the formula to actually find what drift velocity is has to take several things into account. And I want to talk about some of the things. It is affected by, we've already talked about, it's these collisions. The collisions are really going to impair or impede that speed going along. So it's going to be affected by the number of free electrons. It's going to be affected by the number of free electrons. Now the free electrons are actually going to let me hold off on that. I don't actually want to say that quite yet, so we'll work through it. The number of free electrons, which is a capital N, I'll do all of the relationships at once. And number of free electrons. And N is actually, I can find the number of free electrons by the equation N sub E times A times D, where N sub E is the free electron density. So how many electrons in a given space? Free electron density. And A is the cross-sectional area of the wire. And wires are typically round, so you're going to find the cross-sectional area of a circle. Cross-sectional area of the wire. And D is the length of the wire. Okay, so the speed of it is going to be influenced by my number of free electrons, and I can determine my number of free electrons by the equation N sub E, which is the free electron density. So that's in this given space, how many free electrons are there, but I need to define that space a little bit better by saying what's the cross-sectional area of my wire and what is the length of my wire. So this is a constant, what it would be, but then on top of that I have to define the space. All right, now let's pull all this together. I is equal to Q over T. You already know that. But I can define my charges, which are based on my number of electrons, as the number of, let me write that out here. Charges based on the number of electrons, and we've already established what that is. So what my charge is really the number of free electrons times E, which of course E means the charge on an electron, 1.6 times 10 to the negative 19. So another way of saying it then is I is equal to, and the negative is going to be important because we're going to be talking about velocity here, negative N times E. N is the number of free electrons times the charge on each of those electrons, all over T. I've just taken what I've defined my Q as, number of electrons times E. You've done that a number of times. If I give you the number of electrons, what's the charge on it? You've done that. Well, now we're saying, okay, but those number of electrons do more than provide charge. They also kind of influence how fast this thing is going. Now let's redefine I is equal to, I can redefine my N. It's going to be a negative, I said over here, N sub E A D. That is how I identify how many free electrons I have, what is the density, and oh, by the way, what is the space that it's in. So I'm being very specific about how many electrons I have, times E, because that is still carrying along right here, all over T, but V is equal to D over T. So I is equal to, if I make this into D over T, here's my D and here's my T, so I can take those pieces out and in place of these put my V. So what I have is a negative electron density times the area times the charge on each electron times V, which is my drift velocity, or here is my equation, just showing you where it comes from. V sub D, my electron or my drift velocity of my electrons, is equal to, I'm just moving that over, negative I. The negative just means that my current is going to be flowing opposite my drift velocity, or the speed of these is going opposite in terms of the direction. The velocity of these is going opposite the direction of the current, which of course we knew that, and that's why we had to add that negative at the very beginning. So it's going to be negative I over N sub E, that's my free electron density, times A and E. Okay, so the density tells me how many electrons I have per given space, but then when I throw in the A and the D, that means I'm taking out that space. So now it's just the number of free electrons, and I'm multiplying those number of free electrons times what the charge is. So that's what's going on here. And again, my A is just a part of the volume piece of my density. So you have to put that in to get rid of the volume piece in order to find just the number of free electrons. And I moved all of this over to get V all alone. And so my electron drift velocity is negative current all over the free electron density times the cross-sectional area of the wire times the charge on each particular ion. Okay, this is just an interesting way of looking at how electrons move across a wire. They don't run, and they move more slowly if there's just more getting in the way of it. So let's work through this and just see what this looks like here. So here's the question. When starting your car, 100 amps flow through a copper wire. And this is a constant for a given substance. The free electron density of copper is 8 times 10 to the 28th electrons per meter cubed. So how many electrons do I have in a given space? The cross-sectional area of the wire is 30 times 10 to the negative 6 meters squared. Find V sub D. So let's write down what we know. I know that the current is 100 amps. I also know that my free electron density is 8 times 10 to the 28th electrons per meter cubed. And my area, they figured that out for you, which was kind of nice. I didn't tell you, well, the diameter is this, figure out the area, is 30 times 10 to the negative 6. And we've talked in the past about why is it that they don't use proper scientific notation for these. Why not make it 3 times 10 to the negative 5? It's customary, especially in physics, it's customary to try to leave things in powers of 10 that translate well to the prefixes. So if I wanted to make that instead of meters, if I wanted to make it negative 6 would be micro. Of course, now we're squaring it, so that complicates it a little bit. But just that's the reason why they leave it in negative 6, because it's those powers of 10 that create the prefixes, and it's a comfortable place for physics to land. And then we know that the charge on an electron is 1.6 times 10 to the negative 19. And again, because we're talking about current, because we're talking about charges in current, I don't add the negative in front of that, but that is coulombs. And I want to find V sub D. So V sub D is equal to a negative I all over, wow, it's not a straight line, all over N sub E, A, and E. So that ends up being 100, and I'll put a little negative there, all over 8 times 10 to the negative 28 electrons per cubic meter times 30 times 10 to the negative 6 meters squared times 1.6 times 10 to the negative 19 coulombs. And that's my V sub D. Do all the math on it, and it ends up being a negative 2.6 times 10 to the negative 4 meters per second. Super, super slow compared to the 1 times 10 to the 6 velocity that electrons can have if they're just left to their own devices. In terms of how much that would be over time, that would end up being, give me a second, that would end up being an hour, approximately an hour for an electron to move 1 meter. So yeah, an hour to move 1 meter. They're not flying across the wires here. They're going pretty slowly. So that's how the electrons move through the wire. It's actually complicated because we're using a conductor. And because it's a metal, it's a conductor. Because it's a metal, it has all of those free electrons that are just in the way. And the number of free electrons, the density of free electrons is really dependent on the kind of material it is, but metals have really high free electron density. Copper wire is really one of the best wires that you can use to carry electricity, and that's partly because it does not heat up. It doesn't provide much resistance at all to the electrons traveling over it, so you're not losing a lot of your energy to the resistance. Copper has a resistivity, and we'll talk about that later, of 1.7 times 10 to the negative 8. It's really, really low resistance that it provides. So that's a good thing. It doesn't go fast, but really who cares? It can create a good environment for the electrons to flow, even though they're not flowing very quickly. All right, so now we're going to turn into what is all this relationship between potential difference or voltage and current, and then how do we slow the current down? How do we influence these different factors? And that's going to be throwing resistance in. So the two quantities that affect current in a circuit. Remember, current is the number of electrons that pass through a given point in a given amount of time. The number of electrons that affect, or the two quantities that affect current are going to be, first of all, how much oomph am I getting? Am I pushing them through there very quickly? So that's going to be potential difference. Am I really pulling those electrons toward me? How much pull is created as an electric field because of the potential difference? But then the other thing that's going to slow them down, it's going to provide opposition to these electrons flowing through, is going to be resistance. So you've got these two kind of working in opposition to one another. The voltage is going to try to pull the electrons through. The more voltage, the more pull it has to get those electrons through as fast as possible. Again, current is number of electrons per unit of time. And then the resistance is going to say, whoa, 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 whoa. To do your work here, you gotta slow down. You got to have some opposition here, and think of it as electrical friction. It is slowing down those electrons, so the two are working in tandem but against each other. So in my V is equal to IR equation, V stands for potential difference, and potential difference is measured in volts. And hopefully you know by now that when I say PD, I'm talking about potential difference. I is current, and current is measured in amps or amperes with a capital A. I'll put amps just so that you know that that's what I'm talking about. And R is resistance. Resistance is the opposition to the flow. Think of it as electrical friction. And it's measured in ohms. And the symbol for ohm is the uppercase or capital omega. So it looks like this. This is my least favorite of the Greek letters to create because it never looks good. But this is what omega should look like. Okay, it's like a horseshoe, but it's got those two little hooks on it too. And this, by the way, is where the motion of the electrons does the work. So let's look back to our very first drawing that we did of a battery. And when you look at that drawing, it's kind of pointless. I mean, the drawing is a good drawing, but it is a it's pointless system. It's a pointless circuit because basically all I have is an electromotive force, something that's pushing the electrons through, and the electrons are going through and then go right back to the battery. So it doesn't really do anything, so what's the point? And that's why in the next drawing, we actually attach the battery to, you'll see in this one, we attach the battery to a resistance of some kind. The resistance might be a light. It could be a hair dryer where there's coils that are heating up. So it's something that I am having the electrons do some work. They're flowing for a purpose. Now the resistance, that thing that's going to be doing the work in the circuit, the resistance depends on three different things. It depends on the type of material, and metals have less resistance. That's a good thing. Don't think of resistance as the free electron, the free electron density. Don't think of resistance that way. Resistance is about how it interacts with that particular material itself, not about how many electrons are involved in this thing. So it's the type of material, and metals have less resistance than nonmetals. Silver has the least resistance of all, and I will be posting some of the charts that have these constants on them. Silver has the least resistance of all, and so it's actually probably more cost effective in terms of the energy you use to have silver wires because they have such a low resistance, but copper is only marginally higher than silver and a lot cheaper. So copper is the wire of choice for electric circuits. So it depends on the type of material, the length of the material. The more the electrons have to interact with this resistor in terms of length, the more resistance is going to be built up. And the same thing with the area of the cross section. Okay, so the formula for resistance then is going to be, you're going to take all these factors into account, and resistance is equal to rho times L over A, where rho is the constant that comes from the type of material, and of course L is the length and cross-sectional area is the A. Okay, so let's work through what this looks like. If an automobile starter has a resistance R of 0.1 ohms, how much current flows through the starter when it's connected to a 12-volt battery? And how much charge passes through the starter if it runs for 10 seconds? So the first thing, I'm going to be using my V is equal to IR equation in order to find the current. So V is equal to IR. I know that my voltage is 12 volts. My I is what I'm looking for, and my R is 0.1 or 0.10 ohms. And when I multiply, when I move that over, I end up with I is equal to 120 amps. 120 amps. And then I'm supposed to find how many electrons that is in 10 seconds. So it's going to be I is equal to delta Q over delta T. Now that's not going to get me electrons, but my total charge can give me the number of electrons if I just use dimensional analysis. Oh no, actually, I'm sorry, it's only asking for charge. So I'm asking for Q. It's not asking for number of electrons. That was your homework from before. So my 120 is equal to delta Q all over 10. So delta Q is equal to 1200 coulombs. All right, let's try another one. In the human body, most electric current is caused by the movement of sodium positive, N positive 1, and potassium, K positive 1 ions, and chlorine, Cl negative 1, and magnesium, Mg positive 2 ions. The resistivity, rho, of the body tissue depends on the concentration of the ions, and it is approximately 5 ohms times meters. That's the resistivity, and that's the unit for resistivity, ohms times meters. And that should, I actually think it's supposed to be meters to the -1. Give me a second here, and ohm times meter. Okay. I'm not going to bother with that, but this is the unit for resistivity is ohms times meter, and I know that that is correct, so we will just leave it at that. I was trying to get it off of this equation up here, and I should not have been doing that, so I apologize for that. So just ignore my fumbling around with this. The resistivity is ohms times meters. And that actually does make sense. And I need to do that now because I messed up. So if I'm trying to find resistivity, rho is equal to R times A over L. And A is going to be meters squared, and L is going to be meters. And so that's why that is going to cancel out, and rho is measured in ohms. And so that's why, resistance is measured in ohms. So that's why rho is ohm times meter. I was trying to use my just plain resistance to get that, and I just messed up. All right, all of that to say the resistivity of the body is approximately 5 ohms times meters. Estimate the electrical resistance of the lower leg of a human. Calculate the current through the leg if it is connected to a 100 volt power source. Now, you're not given the data about that, so you can assume that the leg is 0.3 meters long and has a radius not diameter, a radius of 5 centimeters, which of course is going to be 0.05 meters. So I need to find the area first. A is equal to pi r squared, which is going to end up being, when you just throw the math in there, it's going to be 7.85 times 10 to the -3 meters squared, because it's area, so it's meters squared. So that's A. And it told you that the resistivity is this and the length is this. So my resistance is going to be 5 times my length, which is 0.3, all over my area, which is 7.85 times 10 to the -3. So the resistance is going to be 191 ohms. I told you I really hate making this symbol. 191 ohms. Then if I throw it into V is equal to IR, I get 120 volt is equal to the current through the leg, so I need to know what I is, that's what I'm looking for, times 191. And so my current through the body is 0.628 amps. And you know, that doesn't sound like a whole lot. Doesn't sound like a big deal at all, but unfortunately, that much resistance actually it could be lethal. That much resistance could be lethal. It's actually about 6 times greater than lethality in current. And in fact, let me talk to you about that. That's the very next thing that I want to do with this is I should have flipped it over, is the graph. I want to show you the graph on how you can identify. This is a logarithmic graph that will tell us what you can expect from current through the body. It can be super lethal, super fast, super easy. So let's look at some of the numbers that go with this. So just make for yourself a nice straight line to create a chart or a graph for this. And I need to create a straight line, so I'm going to get my straight edge here. So I have a nice straight line. Try to make it straight and horizontal while I'm at it. And I'm going to start way back here. I am going to call this 100 microamps. And I'm seeing that this is already 35 minutes long, this video. So I think I'm going to hold off, and I will just introduce that tomorrow. And then I'll introduce it, yeah, for Friday's lesson. This has been long enough. Your homework for tonight is going to be, and again, I will fix all that, so you should have all of the correct homework on there that you need. Give me just a second so I can pull up the homework for you. I should have had that handy, I'm sorry. Well, like typical, I am going to have to get back to you on that because I don't have the homework right in front of me, which I thought I did, so I apologize for that. I will post for you what the homework will be. It's gonna be two different things that we're doing at once because this is a longer class time for the face-to-face students, so it's going to be longer homework for you, but I will post that for you and let you know what it is. All right, let me know if you guys need anything. I've kind of been a little bit distracted here, and I apologize for that, but what you've been given is what you need to move forward with this, so let me know if you're running into any snags. All right,